How are you all? I hope you all are doing well. Today we are here with one of the important topic from partial differential equation, which is a Green's function, which is very much important for CSIR NET exam, GATE exam and SET exam and other competitive exam too. So in my today's lecture, I'm going to explain to you all the Green's function first, and then we are going to solve some previous year questions from CSIR NET exam. Already I uploaded plenty of the videos on my channel which depend on the Green's function. So if you wanted to check this video, you may check it into my playlist. Now let's get start our today's topic, which is a Green's function. Green's function means we have a homogeneous differential equation, okay, which is in the form of Ly which is equal to 0. Because right side 0, that's why we call it as a homogeneous differential equation of order n. L is a differential operator and which is defined that L is here differential operator with respect to y of order n, and which is defined as L which is equal to p naught of x, which is a polynomial with d raised to n by dx raised to n the derivative of p naught of x, n minus 1 differentiation of a p1 of x, and up to n minus 1 of a polynomial of a differentiation d by dx plus pn of x. Okay, so the L which with respect to y, so which is equal to 0, then we call it as a homogeneous differential equation of order n. Okay, so function p naught to pn are continuous on closed interval ab. Okay, so these polynomial functions are continuous inside this closed interval, and p naught of x which need to be a non-zero. Okay, that not p naught of x need to be a non-zero. When it is a non-zero, then only we can define the polynomial over here on closed interval ab. Okay, so the remaining vk of y which is equal to 0, k is equal to 1 to n. Okay, so this is the everything definition. Just I wanted to explain the form of a non-homogeneous differential equation and the polynomial of a nth differentiation. Now let's get start our today's question. We're going to learn first of all what we have given in our question, and then we'll go through the detailed solution of our question. Here in our question, we have given green function of a boundary value problem, which is a y dash double dash which is equal to 0. Okay, that means f of x is a given function which is equal to y double dash which is equal to 0, and the boundary condition also defined here. So the first boundary condition is the y of 0 which is equal to 0, and second boundary condition y of L which is equal to 0, or you may take L as 1 also. Okay, so this is the boundary condition for that particular value that we get the y as a 0. Okay, and we have to find the Green's function of our boundary value problem. Okay, so try to remember from Green's function for finding the boundary value problem, given using boundary value problem for finding Green's function. What we do first of all, what we do, we try to convert our boundary value problem into freedom integral equation of a second order, and with the help of a Green's function we solve this differential equation. Okay, so first of all we need to check whether Green's function exists and unique is there or not. Okay, so when we say that a Green's function exists and it is a unique, when our given function has a trivial solution, that means our given function gives us a trivial solution, then we say that our given function gives us a unique and existence of a Green's function in our boundary value problem. Now let's check whether our boundary value problem is having a unique solution, trivial solution or not. Okay, and if it exists a trivial solution, then we say that our Green's function which is exist and unique. Okay, so now let's check whether our boundary value problem is having unique solution or not. Okay, so here we have y double dash which is equal to 0. So try to find out the solution for our equation y double dash which is equal to 0, double differentiation which is equal to 0. So convert it into the form of a polynomial. So we have to check only whether it is having trivial solution or not. So y double dash 0, that means we always take it's a d square which is equal to 0. Okay, that means a d square or m square which is equal to 0, because we have to find out first of all root of our boundary value problem. Once we get the root of our boundary value problem, then we find it's the solution. So d square is a 0, that means we have the value for d is a 0. Okay, that means d is a 0 0 because we have two power, no? That's why we are getting two roots. D square is a d is equal to 0 and 0. We got the two root here. So when we have repeated root, then in our differential equation, then we write it as the solution as y of x is equal to c1 plus c2x into e to the power m1 x. Okay, when it is a repeated root. When it is a distinct root, then we write c1 e to the power m1 x plus c2 e to the power m2 x. Okay, and when it is a complex root, then we write c1 cos m1 x plus c2 sin m2 x. Okay, so these are the e to the power x. So this is the way to write solution of our differential equation. So I got the d is a 0 0, which is the two root. So that means m is a 0 0 is a two root. Now substitute it into the solutions. We will get the y of x, which is equal to c1 plus c2x e to the power m1x. m1 means d1x. We have here both root 0. So e to the power 0 into x. E to the power 0 into x means 0. E to the power 0 always 1. Okay, because whenever 0 goes to the power, it gives us value 1. So I got the solution of our boundary value problem y of x, which is equal to c1 plus c2x. Okay, so this is the solution, but we have to check our boundary condition, and we need to find out the value for c1 c2. So if it gives a non-trivial solution, okay, it gives a non-trivial solution, then we cannot apply boundary Green's function. That means there do not exist Green function, but it gives us a trivial solution, then there exists always a Green's function. Okay, now we're using boundary condition. First boundary condition is here y of 0, which is equal to 0, y of 0 which is equal to 0. So apply y of 0 is equal to 0, input instead of x is a 0. So y of 0 which is equal to c1 plus c2 into 0. So y of 0 is equal to 0, which is equal to c1 plus 0. That means I got the c1 is 0. Similarly, apply next boundary condition. This one is the first boundary condition. Second boundary condition, y of 1 which is equal to 0. Okay, so y of 1 which is equal to 0, then we put here y of 1. So y of 1 which is equal to c1 plus c2 into, instead of 1 we have to put here, okay, x we have to put 1, because here instead of x we have 1 here. So replace x by 1. So y of 1 which is equal to c1 plus c2 into 1. Okay, now put y of 1 0 which is equal to, and c1 is also 0 plus c2. This gives us a c2 which is also 0. Okay, so I got the value for c1 0 and c2 also 0. Now substitute both of these value in our y of x. Then let's check what the value will come. Okay, c1 is 0 plus c2 into 0 is a 0. That means I got the y of x which is equal to 0, and which is a trivial solution, which is a trivial solution. And whenever our boundary value problem gives us a trivial solution, then we say that Green's function exists and unique. Okay, so now this is the only part here that we have to check whether Green's function exists there or not. Okay, and if once Green's function exists, then we have to apply the following steps. Now let's check the steps. So in our 4 steps, what we do first? In first step, what we do? In each interval, that interval which defined in our boundary condition. Okay, so we have to create interval using boundary condition. Okay, that AT TB. Okay, we have 0 to 1 interval there in our boundary condition in our example. So here we have interval A to T, T to B. Okay, and the function g of xt, Green's function, we have to consider as a function of x. Okay, which is the solution of our given boundary value problem. Then we write it as a L of g which is equal to 0. Okay, as we have Green function as a g of solution of a Green's function as a y of x which is equal to c1x plus c2. Okay, in our example. So now what we do here, we convert our solution in the form of Green's function like L of g which is equal to 0. That is a a1x plus a2 and b1x plus b2. Okay, so I considered here as a Green's function g of xt as a a1x plus a2 and b1x plus b2, and which is having boundary condition 0 to t. Okay, 0xt and tx1. Okay, 0 to 1 limit is there, that's why I converted to 0 to t and t to 1. Okay, So this is our first condition says that. So we have to translate our condition into example. Now second condition, it says that g of xt is a continuous and has a derivative with respect to x up to the order n minus 2. Okay, so we have to differentiate our g of xt in the interval we have given in a boundary condition. So which is a axb here. Okay, so always remember we have given different boundary condition every time that interval for our different derivative, it will be vary as per the boundary condition. Okay, now second third condition, it says that n minus 1 the derivative of a g of xt with respect to x at a point x which is equal to t has a discontinuity of a first kind, and the jump being equal to minus 1 upon p naught of t. Okay, so minus 1 upon p naught of a t, which is the p naught of a t is the coefficient of the nth term. Okay, nth derivative of our uh, boundary value problem. Okay, so as we have the boundary value problem, which is a y double dash which is equal to 0, y double dash which is equal to 0, and a p naught of a t which is the coefficient of a y double dash of a 0, that means here p naught of a t we will get the 1. Okay, in our example I'm explaining example with respect to this condition. Okay, so how we can apply this condition to our example. So minus 1 upon p naught of t we have to find out here, and then we have to substitute it to the is the first derivative, n minus 1 the derivative. Okay, that means we have double differentiation, that means a 2 minus 1 the derivative. 2 minus 1 the derivative means single derivative of our Green's function. Okay, and remember always we build that Green function using our boundary value problem. Okay, and always think about that double differentiation as a nth derivative. Okay, and we want the n minus 1 the derivative of y double dash. Okay, at a point x is equal to t plus. Okay, and x is equal to t minus of d raised to n minus 1 of g upon dx raised to n minus 1, x is equal to t minus. Okay, and for the condition we have to define the Green's function at the end using the value for a b c d, the constant which is exist in our Green's function. Okay, so first of all we have to find out the all constant, need to substitute in our required Green's function, then we will get the g of xt as your Green's function. So here is all the steps. So it seems like quite confusing to you all right now. Because of that, these are the quite theoretical concepts. Once we apply this one into our equation, that one can be easily to verify. Okay, so now let's get start our solution, that we can see how we can apply this condition to our solution. Here you all can see, so I firstly define here our given boundary value problem and check it here whether it is a exist trivial solution or not. Okay, and it is having trivial solution, so hence Green's function exists and unique. Now by using that y of x or the condition we have here, okay, c1x plus c2, so we have to define Green's function using this. Okay, g of xt using this, which is just a1x plus a2 and b1x plus b2. Okay, but now we want the first condition. Okay, the interval where a1x plus a2 which is defined. Okay, and the interval where b1x plus b2 which is defined. Okay, so we have the interval as a boundary condition 0 to 1. Okay, 0 y of 0 is equal to 0, y of 1 is equal to 0, 1, y of 1 is equal to 0. That means we have condition boundary condition 0 to 1. Okay, so we have to define g of xt in the interval of 0 to 1. Okay, now first we need one interval for this, second interval for this. So for first interval we write at a 0 x and t, because in the function g of xt in the form of x and t, so we need to know the both value x and t. That's why I define 0 xt and tx1. Okay, tx1 for this in Green's function. Okay, so I got the two different boundary condition, using boundary condition, two different limit for x and t. Now let's define the Green's function over here. So I define Green's function at to tb as per our condition, as Green's function should be given in the boundary function value problem. It's a g of xt is equal to a1x plus a2 b1x plus b2. So 0 xt and a tx1, I taken 1 here. Okay, so I got the Green's function over here. So this is our required Green function. But as we can see here, it seems like that we have some constants a1, a2, b1, b2. So we have to find out these constants. Okay, for finding these constants, we always know that for finding any constant in our differential equation, what do? We differentiate it with respect to that variable. Okay, in our function. Okay, so once we differentiate, then we get the value for these constants. So for finding the value for a1, a2 b1, b2. Okay, now let's work for the value for a1, a2 and b1 and b2 as per the given steps in our Green's function. Now in our second step, what we do, g of xt is continuous at n minus second derivative, okay, of a g of xt. N minus second derivative means y double dash we have here, which is equal to 0, our function. Y double dash of 0 means n minus second. That means we have two times differentiation. Okay, so we have given 2 times differentiation, and then we want the n minus second the derivative. Okay, that means 2 minus 2 times differentiation. We want 2 minus 2 times differentiation for our Green's function. Okay, so 2 minus 2 times differentiation means 0 times differentiation, and 0 times differentiation means we do not have to differentiate our Green's function. Instead of a y double dash, if we have y cube, y third derivative of y, fourth derivative of y, so we have to subtract it here, and then we have to differentiate further. But as we have double derivative only, so what we do, we just take n minus 2 derivative, so which is a 0. That means we have to keep g of xt as it is. It's continuous at x which is equal to t. If g of xt which is a continuous at x which is equal to t, that means it's a left hand limit and right hand limit which always equal. Okay, continuous, definition of a continuity you need to know here. Okay, so if we apply that definition of a continuity, that says that the left hand limit and right hand limit need to be equal. That means g of xt at x which is equal to t minus and g of xt which is equal to x which is equal to t plus need to be equal. Okay, and as we know, g of xt at x which is equal to t minus, that means the value which is smaller in our Green's function, which is a1x plus a2, because which are having value 0xt. Okay, 0xt, which is a smaller value. That's why it is x is equal to t minus for smaller value, and this value b1x plus b1x plus b2, which is the value for tx1. Okay, this is the value for tx1. So this one is a quite bigger value than this. That's why positive value it goes here. And xt, we need to replace x by t here. Okay, and x by t here. So g of xt is a1x plus a2, and x by t means a1t plus a2. And similarly here b1t plus b2. Okay, now go for the other values for a1, a2, b1, b2. Okay, so take these two terms at one side. We'll get the b1 minus a1t plus b2 minus a2, which is equal to 0. Okay, so consider b1 minus a1 which is equal to c1 t as it is, b2 minus a2 is equal to c2. Okay, that is a ci which is equal to bi minus ai. Okay, so I consider here c1 and c2 as a b1 minus a1. Okay, because it's look quite bigger and for confusing to find their values, so that's why we consider it c1 c2, and later on you may consider it back. Okay, b1 minus a1 is equal to c1. So now second step, what do we do in the second step? Second step, we take n minus 1 the derivative of a g of xt of a first kind of a discontinuity. Okay, that means n minus second 1 the derivative of a g of xt has a first kind of a discontinuity. That means we have y double dash which is equal to 0. That means 2 minus 1 means 1 the time we have to differentiate our g of xt. Okay, and as we have g of xt as a1x plus a2, that means differentiate with respect to a1, you will get the x with respect to, okay, then you will get the a1 and you get the b1. Okay, condition 0xt tx1, it will remain same. Okay, then what we do, we take their subtraction for g of xt as x equal to t plus minus g of xt as x t minus, and which is equal to minus 1 upon p naught upon t. This is the condition which we define third in our defining Green's function. Okay, these are the condition you need to remember. dg by dx at x equal to t plus minus dg by dx x equal to t minus, which is equal to minus 1 upon p naught of t. Okay, so dg by dx is equal to x to t plus, what it is the value which is the plus. For plus you will get the b1, for minus you will get the a1, because smaller value it always goes to minus. So a1 here, b1 here, which is equal to minus 1 upon p naught of t. So p naught of t is a coefficient of our boundary value problem. Okay, nth differentiation coefficient. So the coefficient for nth differentiation is 1 here, so minus 1 upon 1, which is a minus 1. Okay, so b1 minus a1 is equal to minus 1. Now this is the time to define the Green's function using our boundary condition. So we have given boundary condition g of 0 is equal to 0, g of 1 which is equal to 0. Okay, so g of 0 which is equal to a1 into x plus a2. So what do we got here? 0, x is a 0, so g of 0 is equal to a1 0 plus a2. Okay, so a1 it will be get 0 because g of x is a 0, x the value for x is a 0 here, so x g of 0 it comes here, so a1 0 it will be 0 plus a2. So g a2, I got the value for a2 which is a 0. Okay, and again we have g of 1 is 0, so g of 1 x instead of x is 1 here. Okay, so keep instead of 1 el you can put 1 or el, both will doesn't matter. Okay, both will be remain same, it doesn't matter, because this is just a constant. G of el which is equal to b of 1 plus b2. Okay, so 1 1 it is here, so g of 1 is a 0, so b1 plus b2 here, b1 el plus b2. Okay, so you may keep it same or you may find it. Okay, it nothing matter. If you wanted to keep here, keep it. If you wanted to put here 1, put it. Okay, nothing matter. In our second condition we have c1t plus c2 is equal to 0, that means b1 minus a1t plus b2 minus a2 which is equal to 0. Now as we have a2 0 and a2 is equal to 0 and b1 minus a1 which is equal to minus 1, in our previous condition we got this value, so put it here. So we'll get the b1 minus a1 minus 1 into t plus b2 minus a2, it will be 0, so b2 I got the value t here. Okay, b2 is a t. Then b1 is equal to minus t by l or minus t by 1. Okay, so el or 1 you may take anything, so put it here, b2 in 0 is equal to b1 el plus b2. Okay, so you will get the b1. So b1 minus a1 is equal to minus 1 as we have here. Okay, b1 minus a1 which is equal to minus 1, we found it already in first differentiation. Okay, so b1 put here minus t by l, a1 is equal to minus a1, keep it, and minus 1. Okay, find out the a value for a1 which is minus 1 plus t by l, and which gives us l minus t upon l. Okay, this is the value for a1. So I got the value for b1, I got the value for a1. Okay, now put all the value for b1, a1, b2, a2 in our Green's function. Okay, so what we have here, a1x plus a2, so a1 l minus t into x, l minus t. Okay, l minus t upon l, that means 1 minus t upon 1 into x plus b, and b is a 0 here. Okay, so b which will be 0, a1x plus a2, so a2 it will be 0 here, and b1x plus b2, and b2 it is here as a t, and b1x will be minus t upon l into x. Okay, so here minus t upon l, or 1 you may take anything. Okay, minus t upon l into x which is plus t. So a1x plus a2 0, b1x plus b2 is a b2 is which is equal to t here. Okay, so that means solve the g of x t in simple form, l minus t upon l into x, and we have interval 0 x t, and l minus x upon l minus t, we have entered tx l. Okay, so this is our required Green's function. Okay, so as we first of all discussed to verify whether Green's function exists or not. Okay, so as we got the trivial solution for our boundary value problem, so we said that Green's function exists and unique here. Okay, so then after we defined the Green's function a1x plus a2, b1x plus b2, and then at the end we got the value for a1, a2, b1, b2, and we substituted all these value in our Green's function, then we got the Green's function here. Okay, so this is all the process for finding the value for Green's function. I hope you all have understood this one. Okay, quite easy to understand, just little bit part of calculation. So even after, if you found anything difficult, let me know in comment section. I will come up with some other videos. So thank you everyone. Thank you for my today's lecture.